Hello students. Welcome to the YouTube channel, Physics Simplified. Here, we will understand numerous concepts of physics from a numerical perspective. So, without any further delay, let's jump into the discussion. Topic of discussion for today's video: magnetic field due to a moving point charge and forces between two moving charges. In this problem, two protons are moving parallel to the y-axis, but in opposite directions with the same speed v, where v is negligible compared to the speed of light. This is shown in the given figure. We need to find and compare the magnitudes of the electric and magnetic forces acting on the upper proton. Let us now identify the concept we need to solve this problem. By using Coulomb's law, we can determine the electric force acting on the upper proton. By using Lorentz magnetic force, we can determine the magnetic force acting on the same upper proton. Now, we will set up the procedures in final equation to solve the problem. Since the Lorentz magnetic force acts on a charge only when it is moving inside a magnetic field, hence, we must first find the magnetic field that the lower proton produces at the position of the upper proton. Here the lower proton is the source. This can be done by using the reference equation, vector B is equal to mu0 by 4 pi times q vector V cross r hat divided by r squared. The unit vector r hat for this problem is from the lower proton to the position of the upper proton along the positive z direction. By using Coulomb's law, we obtain the electric force on the upper proton, and it is given by F suffix E equals 1 by 4 pi epsilon 0 times q squared divided by r squared. Since the two charges under consideration here are protons, hence, the electric force is repulsive in nature, and it is vertically upward, that is, in the positive z direction. Since the lower proton is moving in the positive y direction, hence, its velocity is given by vector v is equal to v j hat. According to the figure, the unit vector from the lower proton to the upper proton is given by r hat is equal to k hat. Now, by using the right-hand rule for the cross product of vector v and r hat, we find that the magnetic field vector, that is, vector b, produced by the lower proton at the position of the upper proton, is in the positive x direction. This can be done as follows. Vector b is equal to mu0 by 4 pi times q v j hat cross k hat divided by r squared. Since the cross product of j hat and k hat is equal to I hat. So, vector b is equal to mu0 by 4 pi times q v divided by r squared I hat. Since the upper proton is moving in the negative y direction, hence, its velocity is given by vector v is equal to minus v j hat. So, the magnetic force acting on the upper proton is vector f suffix b is equal to q vector v cross vector b. This is the vector representation of the Lorentz magnetic force. Substituting the expressions of vector v and vector b, we get vector f suffix b is equal to q within second bracket minus v j hat cross mu0 by 4 pi times q v divided by r squared I hat. Or vector f suffix b is equal to minus mu0 by 4 pi times q squared v squared divided by r squared times within first bracket j hat cross I hat. Since cross product of j hat and I hat is minus k hat, therefore vector f suffix b is equal to mu0 by 4 pi times q squared v squared divided by r squared times k hat. This magnetic force on the upper proton is also vertically upward and repulsive in nature. Now we will find the ratio of the magnitudes of electric and magnetic forces on the upper proton. Substituting the expressions of F suffix E and F suffix B, and then simplifying and rearranging, we get F suffix E divided by F suffix B is equal to 1 divided by mu 0 epsilon 0 V squared. But mu 0 times epsilon 0 is equal to 1 divided by c squared, where c is the speed of light in free space. By using this relation, we get from the above equation, F suffix E divided by F suffix B is equal to c squared divided by V squared. This is the answer for this problem. Remember, when speed of the proton is very small, compared to the speed of light in vacuum, the magnetic force is much smaller than the electric force between the two interacting protons.